climate change signals so that we can look at climate variability combined with likely future climate change impacts. And our climate change is factors and or method is being drawn from the NARCLIM project. NARCLIM has developed a suite of regional climate models specifically for New South Wales. One of the most important parts of this project is quality assurance of the stochastic data. Rainfall in particular is really challenging to simulate. It varies a lot spatially, so you can get rain falling in one location and nearby no rain at all. It also varies in time. There isn't a very strong correlation between rainfall in one month and the next in most of New South Wales. It varies from year to year. And on top of that, small biases in rainfall can cause large biases in simulated flows. Our assessment of the climate data is looking at a really wide range of different metrics. And I'm not going to go into those today, but I'll just show you some sample results for one basin, which is around Bega or Trooros. Here I've shown average monthly plots for the observed climate data and the stochastic data. The top two show you P&T and rainfall. The observed is in blue and the stochastic is in orange. The match between these in terms of average monthly values is very good. But the real test is how did this stochastic data perform when we put it into the hydrological model? And that's what the bottom plot shows. As you can see, there are some differences, but overall there's a really good agreement in terms of those mean monthly flows. And while I've not shown those results here, the stochastic data also catches extremes, high flow events and periods of long low flow periods that we haven't seen in the observed record. So this data set, from the quality assurance, we have a lot of confidence in the method, and Dushmanto, I'm going to hand over to Dushmanto to talk about how we're putting this all together and looking at the results.
Thank you, Rachel. Going back to the regional water strategy development, we have used a very considerable 12 different regions in New South Wales to develop the regional water strategy for each of those. There are 5 steps in that. The first step is to identify the opportunities and challenges for each region. And second, step 2, to understand the future water need of each region within the planning horizon of 20 to 40 years. Then identify various options, both infrastructures and policy options, to meet the challenges and aspiration of each region. And at that stage, the draft strategies are put into the public consultation. That would be in public exhibitions, and people, all the stakeholders would be consulted to get their views on the various options. And once that is done, then we'll have to assess each of those options or combination of those options and their sequences with existing commitment, reform, and infrastructure projects. And based on that, the final regional water strategy for each of the regions would be developed and released. And then based on the priorities of those options, that step 5 would be the implementation and monitoring of the final strategies and review it regularly. So these are the key 5 steps, and modeling plays an important role in many of these steps. So I'm going to take you through that. So river system modeling is essential to the development of regional water strategies for whole New South Wales. So we use the river system model, which is a combination of physical processes as well as the management processes that happen in a river system. There are a number of components of the model where we use the climatic input, for example, for runoff generation, for climate-based crop demand model, for estimating the water demand for urban sector or for environmental water demand. For each of those components, we need to use both all three input data set that Rachel has described about. It's approximately 130 years of instrumental climate record. Then we use 10,000 years of paleo stochastic climate record, and then that another 10,000 years of based on the NARCLIM climate projections together with the stochastic climate. Initially, we used the current condition river system model. We have got the current condition model for all our valleys. For some of the valleys, we had to build a new source model. For example, for all the coastal areas, we have built a different source model to support the development of not only the regional water strategy, but various other policy and strategy framework for the New South Wales government. Once we run it through, that allows us to understand the condition of the regions, not only for the instrumental period, but also for the long-term climate. And on top of that, for the climate projections, with the climate projections, how those conditions would change. Then we bring the different options, and it could be infrastructure options or the policy, operation, and management options, or it could be a combination of those into our baseline model, and we build a scenario model, and scenario model again are run through the climate data set of the stochastic and climate projection data set, and we use a different sets of metrics to evaluate the output of this base case model and the options model to understand, to quantitatively assess different options. So that means it requires lots of modeling. For example, for base case, with the current condition and current operational rule, we need to do each of those models. We have got 12 regions, and we got 18 different river system models to support the development of the strategies for those 12 regions. And for each of those, we need to do at least 2 10,000-year run and also 130 years run. Then when it comes to options modeling, we need to have this options model or the scenario model, or what we'll be calling the portfolio model, with combination of different options. We again need to run through the series of stochastic and climate projections data set. For that, instead of using 10,000 single sequence, we generate 1,000 replicates of 40-year climate duration climate to align with the planning horizon of the regional water strategies of 40 years. And so that means for each of those options, we have to do 2,000 replicates run with and without climate projections for each of those options model. And that would enable us to evaluate, quantitatively assess how the condition of the region would improve if we implement those options in the region. So there are many challenges for undertaking this scale of modeling. We have many regions to model. As I said, we got 12 regions with 18 different river system models, and sometimes some of the system we have to also run it to provide the feedback to the upper region. For example, in a southern connected system, we have to run the Murray and the Murrumbidgee model to provide the feedback to the Snowy system, and then again run the Snowy system, and then run Murrumbidgee and source model. Same thing goes for Bowen-Darling system. On top of the climate projection scenarios. For each region, very large size of input. So we got each of those single time series of daily data set of 10,000 years. So we use the Pat's Point climate data set. That means we got for each of those regions at least 40 to 60 minimum of the climate time series. For some of the regions, it could be many hundreds. For each of those regions, we have to do 40 to 50 simulations with single sequence of 10,000 years of climate input for base case and options modeling. And then we also have to do 40 to 50 simulations with 1,000 replicates of 40-year duration. So some of the models have a very high computational time for each of those simulations. For example, our border source model, border river source model takes about 5 days. Same thing for the Namoi. You have heard from Michael Sugianto how complex the Namoi source model because of floodplain harvesting, detailed farm scale modeling, and it takes around 5 days for us to do the single simulation. Source Murray model takes around 10 days to do a single run. And then we have to process large set of output to provide, to support the assessment of different options using different set of metrics. how we have addressed these challenges for handling the large input and output, also for preparing the assessment framework. We have developed a series of automated Python-based workflows for handling that. My colleague Aaron Trim is going to take you through the technical details of that, so I'm not going to dwell on that today. We have our ordinary desktop, even if it is the best one, it would not be possible to run those 10,000 year simulations for most of our valleys. So we had to get the powerful servers with at least 48 CPU core. We also need to have very large memory. We have got 512 gig of RAM, and we got around 6 terabyte of hard drive for each of those two servers to enable us to undertake these kind of simulations. In spite of that, some of the runtime we cannot reduce, and because of that, we are using parallel computing for system like Mare, for like border rivers. We are dividing the time period into several segments with a significant overlapping period to avoid any impact of initial conditions, and that way we could reduce the runtime. And also we use the parallel computing to optimize the runtime for 1,000 replicates. So with that, we have been successful in doing this modeling. There are some of the other challenges. Again, my colleague Aaron Trim is going to take you through that tomorrow afternoon, so I'll skip that part. In terms of results, what kind of results we produce and how it has helped informing the development of the regional water strategies. So we have got the best case model, we have got different options for scenario model, we have 1,000 years of climate input, and we produce a series of different output in different formats. Regional water strategy has a number of objectives when the assessments are done for different options. So the three key objectives where hydrologic modeling outputs are used. One is the water security, economic prosperity, and the environmental assessment, protect and enhance the environment. For each of those, we have discussed with our stakeholders. We have then developed a series of questions or series of metrics. We interrogate the results of our hydrologic model through those to quantify the impact or to understand the challenges in the current condition, as well as to quantify the impact of different options if we incorporate those or if we implement those, how that would improve the situation on ground. On top of that, we also provide the output for economic assessment of different options, how the economic benefit would stack under those different portfolios, and that would be used for shortlisting the options for implementation phase. So some of the example of output, how we have used the stochastic output or climate projections to help us understanding the region which we couldn't understand with 130 years of data set. For example, this graph shows the minimum inflow in the system for 24 months with one of the system. The green line shows with 130 years of historical climate. When we incorporate stochastic climate and stochastic climate with climate projections, we can see that minimum inflow would significantly reduce. And if we use those sequences, how that is going to affect the storage volume. This is an example for 1st of July, accidents probability of storage volume. As you could see, stochastic would give us the extreme in the dry and wet end, but in a median, they would be pretty close to the instrumental, whereas if we incorporate climate projection, stories would be sitting a much lower level for much longer time. For example, in 50% accidents probability, we get for these particular stories, we get around 75 gigaliter. 50% of the time storage would be sitting in that range. But when we incorporate climate projections, actually 50% of the time storage would be sitting below 40 gigaliter. And how does it affect the allocations? This is the available water determinations accidents plot under those three conditions. The system was pretty secured under 130 years of climate in terms of town water supply. It has allocated 100% throughout that 130 years. But if we look at long-term climate, we can see that 20% of the time, the allocation would not be 100% without any climate change, which if we incorporate climate change, of course, 50% of the time, we would not be able to allocate 100% to these towns. And we can also look at the supply shortfall for each of those towns. For example, from instrumental, there is no shortfall in those towns. stochastic climate. Because of some drier sequences, we get some shortfall. But with the climate projection, those shortfall is going to increase significantly. For example, Town 3, we didn't have any shortfall for last 130 years, but that would go up for 10% of the time when if we consider the climate projections from NARCLIM is reasonable climate projections. Then we look at other economic aspects like average, the diversions to other sectors. So total diversion, general security, supplementary floodplain harvesting, and all those we can analyze those, and then of course we can look into the end of the system flow, how that would be affected. We can look at the whole range with a 95% confidence limit. So these are for the best case. Then we can look into the options. If we incorporate those options, how those are going to improve. This is another example from one of the systems where we could see options 1 and options 2.
I might have to interrupt you there.
Sure.
Probably reached our time, but we've also got lots of quite good questions. So
sure, yep. I'm very final stage. I just got the final conclusions.
Okay.
I'll leave it there. And the key thing is that we have used a long-term climate data set, not only 130 years of data to inform the regional water strategy. We have done a lot of innovative work, the modeling using such a big amount of simulations, and through this work we have generated wealth of information for understanding water security and to inform the development of New South Wales regional water strategy across 12 different regions. So thank you very much. We have our contact details here if we are unable to answer your questions today. I'd like to also acknowledge the all water modeling team members and regional water strategy team for their contribution to this work, and also University of Adelaide and University of Newcastle to support us developing the stochastic data set for this work. So thank you very much.
Thank you. That was very interesting. So I will ask the top voting question that we had. So that might be a tip for everyone else. If you want your question answered, get your friends to vote for it. There are large discrepancies between the paleoclimatic IPO reconstructions prior to the instrumental period. How did you address this uncertainty?
Would you like, I'll take this one.
Okay.
So that's a really good question. We used a IPO reconstruction published by Henley et al. I can't remember the details of the paper. So that was a combination of processed combination of several different or range of different IPO sequences. And their hypothesis was that by combining these, they would get a more confidence in the outcome. In the end, how we're using IPO sequence is to understand the duration in the different phases. So in some ways that we're not trying to predict exactly on what date it would be IPO positive or negative, but instead just to inform those dwell times, which is a slightly simpler question.
Okay. All right, I'll ask the question that's now shot to the lead. This is from Joel Hall. He asks, we are finding that rainfall runoff models that are calibrated for a particular period do not predict well for a significantly drier or wetter period. Have you observed or adjusted for this?
Yeah, that's a great question. I think still research is going on in that stage. So what we have done is to present the current condition. We have updated all our model to use as best as possible the data up to current to do the calibration of the model. So we have recalibrated all of our model in flow for both headwater and section of the river reaches using data up to current, so that we have considered the behavior of the system that we are seeing at current as best in terms of some of the losses. We have also used the dynamic interaction between surface and groundwater, for example, in Namoi. That way, some of the antecedent conditions are also considered. If there is changes in groundwater conditions, that would also kind of affect the losses. That's how we have addressed that, but we have not done any. I mean, we have not planned for recalibration of the model to take into climate projections. So yeah, that's a currently calibrated model with the current data set, and that represent. And we have already seen that some of the catchment behaviors are changing last 20, 30 years with we are seeing non-stationarity. In the climate non-stationarity, that is something we are taking into consideration in stochastic data generation in the southern system. And by considering the recent 30 years of data set in model calibration, we believe like it does represent some of those changes that's already happening in the catchment.
Excellent. No, well, the questions are still coming thick and fast, so I encourage everyone to find Rachel and Dushyantha at the break. Yes, there's lots to discuss there. But thank you very much.
Thanks, everyone.
Thanks, thanks everyone. Thanks, Trudy.
My pleasure. Okay, I will now like to invite David Wright from the Victorian Department of Environment, Land, Water and Planning. Sticking with the climate-related theme, David's going to present on his hydroclimate data transformation tool. Welcome, David.
Thank you very much, Trudy. Just trying to get up my PowerPoint presentation, which is not coming up, so I'll try my whole screen instead.
You just need to have it open. There.
Fantastic. Can you see my presentation now?
Yep, all good.
Yeah, cool. Fantastic. I will eat a little bit into the break time. Apologies, everyone, as we're running a bit behind schedule. But yeah, hopefully we can have some quick questions too. Good afternoon, everyone. My name is David Wright. I'm in the Surface Water Assessment and Modelling team at DELP. And it's my pleasure today to talk to you about the Hydroclimate Data Transformation Tool. I'll just go full screen. There we go. So to start off with, just going to touch on why we'd want to do a hydroclimate data transformation in the first place. Well, historical transformations allow us to take a longer time series of historical data and adjust it so it has similar exceedance properties to a shorter reference period, such as the post-1975 reference period. We can then apply climate change projections and use the time series for a range of water resources and supply applications. To give you a bit of background information on this, I'll walk you through the timeline since 2006. So before 2006, a single linear factor was typically used to make average flow conditions prior to July 1997 equal to average flow conditions from July 1997 onwards. In 2006, there was a workshop to discuss potential options to improve this methodology. And in 2008, the Realm, a predecessor to Source, the Realm Streamflow Transformation Utility was released, and this assumed a breakpoint. In 2016, DELP released the guidelines for assessing the impact of climate change on water supplies in Victoria. And then in 2019, last year, DELP commissioned HARC to develop the Source Streamflow Transformation plugin. And this ported that functionality from the 2008 Realm plugin to the Source software system. Very recently, November 2020, DELP is releasing the updated guidelines for assessing the impact of climate change on water availability in Victoria. And so concurrent with this release, DELP is also releasing the Source Hydroclimate Data Transformation plugin, also developed by HARC. I'll give you a bit of background on the guidelines for a bit of context so these make sense. Guidelines do a few things for water resources in Victoria. They provide tailored guidance on how to apply climate science for water resource planning applications. They promote consistency in approaches to climate change impact assessment for water supplies. And thirdly, they enable more efficient climate change impact assessments. So the purpose of the Hydroclimate Data Transformation plugin is to allow users to perform historic data scaling and construct climate change projections. And internally at DELP, we'll be using this plugin for a range of projects, including the urban water strategies, sustainable water strategies, and future long-term water resource assessments. Since this is a software conference, I'll firstly touch on installing the plugin. So if you're familiar with installing plugins in Source previously, hopefully this will be very straightforward for you. But simply open up eWater Source version 5.2.0, the beta or greater. Select from the toolbar, Tools, Plugin Manager, navigate to the Community Plugins and install directory and install the HydroClimate Data Transformation plugin. Once you've done that, this is what the screen will look like, and you can then load the plugin, use the plugin just like any other plugin in Source. When you open the plugin in Source, you'll be greeted with this first user interface window with essentially those three options: convert data from realm format, apply historic data scaling, and apply climate change projections. I'll go into these three options in more detail later on in the presentation. There's a user manual for the plugin. So there's the URL on the bottom of the screen. But yeah, we can make that available to you. And if you're wanting to use that as a reference, I strongly suggest that. So the plugin has two main functions. The first of these two functions is to apply historic data scaling. Historic data scaling attempts to construct a reference period from an existing historical data set. This enables two things: generation of estimates of historic climate and water availability under historic greenhouse gas emissions, and generation of current and future climate scenarios. The really exciting thing about this is that it allows for longer time series with more natural variability to be used in water resource modeling. Not quite 10,000 years though. If you open up the plugin in Source, this is the first user interface window that greets you. I won't go into too many details, but you're given the option to use two different tools to inform the period A and period B before and after the transformation, or you can set the manual breakpoint date. And you can see here that in this situation, I set that to the 1st of July, 1975. Once you hit next, it'll bring up the next window. And here we're given the option to choose either an annual or a seasonal transformation. And then at the bottom of the screen, we can also choose whether or not we want to do period average or flow duration curve scaling. And we can specify the number of segments with flow duration curve scaling. They can vary between 1 and 1624 with this data set, but we wouldn't recommend going to that many. In fact, for water resources modeling in Victoria, the guidelines, the document I showed earlier on the screen, recommend a couple of things. They recommend an establishment of a post-1975 and a post-1997 historic climate reference period, and application of seasonal decile flow duration curve scaling. So that's 10 segments, just like I've got in the screenshot there. I'll give you a bit of an illustration of applying this historic data scaling. In this figure here, we have some flow data, some stream flow data. In the background, only visible on the left-hand side is the raw stream flow data. And in the foreground is the transform streamflow data in red. Like in the previous slide, I can apply a breakpoint on the 1st of July 1975. So I now have period A before the breakpoint and period B after the breakpoint, and this post-1975 historic climate reference period. When I apply the transformation, so I move from the blue data on the left-hand side to the red data on the left-hand side, you can see those rainfall peaks decrease. And previous example was rainfall. This is now streamflow peaks decrease. So those curves are coming lower. The second function of the plugin is to apply average annual climate change transformations. I've got a couple of definitions up here on the right-hand side for representative concentration pathways and global climate models. If you're not familiar, have a quick read. But the guidelines provide a range of factors for annual climate change transformation for Victoria's river basins. These factors were developed by CSIRO as part of the Victorian Climate Initiative, VICI, and they're supplemented with additional projections available from the Victorian Climate Projections 2019, so the VCP19 project. The plugin allows climate transformations based on a range of things. Firstly, 4 variables. You can apply this to temperature, potential evapotranspiration, rainfall, and runoff. 2 RCPs, those representative concentration pathways. Firstly, the RCP 8.5, and from the IPCC, this is described as a scenario with very high greenhouse gas emissions without additional efforts to constrain emissions. And also the RCP 4.5, and this is an intermediate emissions scenario. The plugin also allows low, medium, and high projections. And these are based on the results of 42 different GCMs, with the 10th percentile corresponding to the low, the 50th medium, and the 90th high climate change projections. You can also use a range of time horizons, the current, so 2020, 2040, and 2065. Interpolation, extrapolation between time horizons is supported. Also is extrapolation. With extrapolation, we just want to keep in mind we want to go no further than 2075. Guidelines also have recommendations for applying these average annual climate change transformations in Victoria. They recommend using RCP 8.5 for water supply planning applications, for using RCP 4.5 for optional sensitivity testing, the use of low, medium, and high climate change scenarios, and linear interpolation and extrapolation up to 2075 to support applications over a 50-year planning horizon. The plugin also has 2 additional pieces of functionality. The first I'd like to highlight today is the peak rainfall transformation. So the peak rainfall transformation is for consideration when individual supply sources are sensitive to changes in infrequent but high intensity rainfall events. So large rainfall events are likely to go up while frequent rainfall events are likely to go down due to the changes in the physical water holding capacity of the air, and this is associated with temperature changes under climate change. So the purpose of this peak rainfall transformation is to reconcile peak rainfall increases recommended by the Australian Rainfall and Runoff with the projected average annual decreases in rainfall presented in the climate guidelines. This is what the user interface looks like in the plugin, just a snapshot. You can see in the top here, we're using the AR&R equation from Book 1, equation 1.6.1. And they recommend a 5% increase in daily rainfall intensity per degree of local warming for rainfall within the range of probability of 1 exceedance per year and an annual exceedance probability of 50% to 1%. So the 5% is typically used, but it's been pulled out as an adjustable parameter in the plugin in case this needs to be changed for future applications. When running this peak rainfall transformation, you'll also need to choose a peak threshold value. And a useful value can be obtained from the Bureau of Meteorology intensity, frequency, duration curves, which are available on the Bureau of Meteorology website. Here's also an example for the peak rainfall transformation. We've got raw rainfall data in blue in the background and transformed rainfall data in red in the foreground. For this transformation, I set a peak threshold of 10 millimeters in the plugin, just like the previous slide. And you can see after the transformation, so moving from blue to red, we're seeing that the peaks are increasing above this peak threshold, and below that peak threshold of 10 millimeters, the non-peaks are decreasing. And you can see that sort of that peak rainfall transformation really working for this month. If you're wanting to know more information about these peak rainfall transformations, please refer to the plugin manual and the guidelines for more details. The second piece of additional functionality I'd like to touch on today is sensitivity testing for seasonal rainfall projections. So just to note that in Victoria, we assume the cool season is assumed to run from April to October, and the warm season is assumed to run from November to March. So across the 42 GCMs from that CSIRO dataset I previously touched on, the cool and warm season rainfall varies for a given annual projection and emission scenario. I'm going to illustrate this with the Werribee Basin on the left-hand side here. I won't go into too many details with this figure, but you can essentially see blue is the cool and red is the warm, and you can see that variability across the GCMs. So because of this variability, there's 2 paired ranges that we can use for sensitivity testing. The first paired range is the combination associated with the greatest increase in cool season rainfall relative to the annual projection, and that's paired with the greatest decrease in warm season rainfall relative to the annual projection. The second pair is the combination associated with the greatest increase in warm season rainfall relative to the annual projection, and the greatest decrease in cool season rainfall relative to the annual projection. Bit of a mouthful there. So both pairs must be utilised to fully understand the potential impact of seasonal projection uncertainty on river or supply system behaviour. For this example on the left-hand side, I've just included an example of some of these paired factors. So for the high scenario, we'd see an 8.5 decrease in cool season rainfall, coupled with a 42.6% decrease in warm season rainfall. And we'd also see the second pair, a 32.3% decrease in cool season rainfall, coupled with a 3.4% decrease in warm season rainfall. So if you're wanting to learn more about this, please refer to the plugin manual and the guidelines for more details. Just to finish, I'd like to highlight some of the additional usability features of the plugin. The plugin comes with a JSON file pre-populated with the relevant factors from the tables and the guidelines, so they're all ready to go if you're wanting to apply this in Victoria. Those factors are fully customizable to applications out of the guidelines. You can load your own JSON or CSV file or manually change them in the user interface. The plugin processes inputs and outputs in either a source or realm format. So that's fantastic for this transition period where we've got a lot of realm and source modeling happening. The plugin generates log files for each transformation that show user-defined parameters, selections, and settings, which is fantastic for reproducibility of the transformations. The plugin is compatible with scenario input sets, as highlighted by the previous presenters. It produces outputs with automated informative naming conventions, so you won't get too lost with all of the different outputs of the plugin. And finally, the plugin has the ability to batch add transformations and perform at least 100 time series transformations at a time. So I'd like to thank Hydrology and Risk Consulting for providing the software development and the documentation of the plugin, the manual. Also thanks to the Hydrology and Climate Science team here at DELP for developing the guidelines, and my colleagues in the Surface Water Assessment and Modelling team for providing technical advice and testing support. For any inquiries, please feel free to email me. Thank you very much.
Thank you. Have you answered this question just in that second last slide, but I will ask it and let you provide a little bit more information. So this one is from Martin Lopesberger. Martin is with Power and Water Corporation in the Northern Territory. Is the plugin Victorian specific? Are there tropical zone options? It sounds like you might be able to customise it for that.
Hi, Martin. How's it going? Yes, so the plugin was developed for Victoria based on the guidelines, but in the development, a lot of parameters have been pulled out. So I can't give you an answer for that for sure, but certainly you could have a look at the plugin and have a bit of a look at all of the different parameters that can be changed. And hopefully you might find it useful for your application.
Excellent. Thank you. Okay, another question's come in then. There's a few now. Okay, in New South Wales, we use, I will say, NARCLIM data.
Mm-hmm.
I noticed you use CSIRO data. Have you compared the two?
So no, I haven't, and unfortunately that sits outside of the work that I'm involved with. So a colleague in the Hydrology and Climate Science team would be much better for answering your question. So I might note that question and get back to you if that's okay.
Excellent. Are the 2020 guidelines available now?
I believe they're very close. So yes, I can't say for sure if they've been made available yet, but I think we're very, very close. I think in the next week or so. Excellent.
Watch this space. And lastly,
yeah, absolutely.
Lydia Seton from Jacobs has asked, is the plugin available for non-beta version of Source?
Hi, Lydia. So the plugin will be made available in a future release, but we're just looking at timelines now to see whether or not that will be included in the next development release.
Excellent. Thank you. Well, I will again give you a virtual clap, David. Thank you very much.
Fantastic. Thank you very much.
Cool. So, excellent. So we will once again take a short break, allow you to stretch your legs, grab a drink of water or chat to your colleagues, and we will get back in about 10 minutes at about 3:25. I'll see you then.